For this lesson, we're going to continue our look at triangles and the trigonometry of triangles. So far in this unit, really we've reviewed some material about right-angled triangles because that's something that would have been covered in a previous course to this one. We've also done a review. We've taken a look at a refresher on sine law, cosine law. Sine law and cosine law deal with triangles that are not right triangles. So up here in the corner I have a right triangle. Down here I have an example of what's known as an obtuse triangle. So there are no right angles here, and in particular the largest angle in this triangle is actually greater than 90 degrees. And so for that reason we call this an obtuse triangle. So that would be an obtuse angle, and then the overall triangle is an obtuse triangle. So how do we go from right angle trig to things like the sine law, cosine law? And one of the key features there is what we do is we make use of the fact that we can actually introduce a right angle triangle by doing something like this. And if I do that, then this side, which I've labeled here as 9 kilometers, this 9 kilometers is actually the hypotenuse of this smaller triangle. And I also have this very large triangle, which is also a right triangle. So there are things that I can do there to tie these things to each other. Today's lesson is really looking at the idea of tying together concepts. Now, the purpose of this lesson is not to go over sine law or cosine law. Those are in another lesson, and they were actually covered in a previous course. What I want to do, my focus for this lesson, is to continue our most immediately previous lesson, where I introduced the idea of an initial arm, which you can see I've drawn here in green, and a terminal arm. Now in that previous lesson, my terminal arm, which is not the one I just moved there, let's see if I can get a hold of the other one. Nope, not having any luck. There, now I've got the one I want. So let's put that back. Okay, here is the terminal arm. In the previous lesson, I was still looking at acute angles, at least to start. But then, when we cross over to here, if my terminal arm is greater than 90 degrees, you can see between the initial arm and the terminal arm, I end up creating this obtuse triangle. So how do we deal with the trigonometry of that? In the last lesson, we did take a look at and we talked about the idea of the related acute angle, and we talked about measuring angles in general. But now we want to apply this to trigonometry. We already know how to do the trigonometry of acute triangles using some of the various rules we've learned about, but we want to extend that in a very particular direction. So that's what I'll be talking about in this lesson. And in this lesson, we're going to be talking specifically about the trigonometry of obtuse angles. Now, I'm going to end up talking about the trigonometry of acute angles because I have to in order to relate that to obtuse angles as well. We will still be making references to our standard model, which makes use of opposite, adjacent, and hypotenuse, which makes use of the idea, there's the angle theta, so the idea that sine theta is equal to the opposite side divided by the hypotenuse, that cosine of theta is equal to the adjacent side divided by the hypotenuse, and that the tangent of theta is equal to the opposite side divided by the adjacent. So that is the mnemonic we use to remember that, in English at least, is SOHCAHTOA. S-O-H-C-A-H-T-O-A. S-O-H-C-A-H-T-O-A. But we want to move away from just thinking about triangles. One of the goals of this course is not just trigonometry of triangles. It is just trigonometry in general. And one of the ways that we accomplish that is we focus less and less on triangles as our end goal. Triangles are a tool that we'll use, but our end goal is to be able to think in terms of the xy plane and to think in terms of the x coordinate and y coordinate of a point, and then an r value, which would be from the origin to that point, the length to that point. So in its barest form, it might look something like this. I should have included the dot there. So there is my point, which has coordinates xy. But I can take that point and that terminal arm, and I can actually represent that in terms of a right angle triangle. So in this case, I would probably refer to that as my angle theta, because here's my initial arm, here's my terminal arm. For the angle theta, the opposite side to theta is just the y coordinate. So the opposite side to theta is the same as the y coordinate of the point, and the adjacent side to theta is just the, and that would be this, that would be the x coordinate of the point. So in terms of what I've got written here, I should then, using these coordinates x and y, I can now write that the sine of theta, where theta is this angle between the initial arm and the terminal arm, the sine of theta, which is opposite over hypotenuse, turns into y divided by r. The cosine of theta is equal to the adjacent divided by the hypotenuse, and that's going to be x divided by r. And the tangent of theta is going to be the opposite over adjacent, but that's the y coordinate divided by the x coordinate. I'm also going to mention right now, some of the writing here might get a little sloppier than usual. I think it's because this slideshow, this presentation, has a lot of graphics in it, and even though the graphics are not particularly complicated, this poor little and old tablet computer that I use for these lessons, combined with some of the limitations of the smart notebook software that I use for transcribing these lessons, it doesn't deal well with too much graphics, and so it slows down. The stylus actually starts to fall behind me, and as a result, my handwriting suffers even more as a result. So, putting all of those relationships together, I start off with an initial arm, which we don't normally draw. We normally just draw the terminal arm. And this terminal arm leads to some point which has coordinates x and y. If I know the x coordinate and the y coordinate, and I either draw this triangle or I just visualize it, the length of the terminal arm, the length of the hypotenuse, can be determined using the Pythagorean Theorem. So r squared is equal to x squared plus y squared, and of course r is always positive because it measures a distance, and so when you take your square root, you're going to take the positive square root. Your sine, cosine, and tangent, instead of thinking of those strictly in terms of opposite and adjacent, we can start to think of those in terms of the x and y coordinates. And something that's missing here that really needs to be labeled here is the angle theta. The angle theta is here. It's near the origin. It's the angle between the initial arm and the terminal arm. So I'm immediately going to take that definition and try to apply it to something quite different, because now I'm referring to the point -4, 3. So instead of being in quadrant 1, I'm going to move over to quadrant 2. So let's see what we get. So -1, -2, -3, -4, -5, and 1, 2, 3, 4, 5 for labeling my axes and my scale. -4, +1, 2, 3. So there is the point that I'm interested in. let's go ahead and put an arrow there. So that represents my terminal arm. So from there, my angle theta would be measured from the positive x-axis. That's my initial arm. This is a point in standard position. So I'm always assuming that I start here on the positive x-axis, which means my angle theta would be there. So I'm trying to measure that angle theta. Now, it gets a little tough when you think about this because, well, how do I draw the triangle that goes with this? Do I draw the triangle down to here? Do I draw that triangle to here? Do I draw the triangle to here? And one thing I want you to notice is, take a look at the angle theta as I try these different triangles. Do these different triangles actually have anything to do with the angle theta? And the answer appears to be no. The angle theta is completely independent of where I choose to draw this last leg of the triangle. So I'll just put it there for convenience, but you need to understand that it doesn't actually matter. What we have here is the point, which is at -4, +3. I've chosen this specifically to make it easy, so we can use the relationship, which is that r squared is equal to x squared plus y squared. So we get r squared is equal to x, which was -4, but it's -4 all squared, plus y squared, which is +3 squared. We end up with r squared is equal to a total of 25. R is equal to plus or minus the square root of 25, but we know that r has to be greater than 0. So we end up with a final r value of 5. I chose a Pythagorean triple in order to do this because I wanted numbers that worked out nicely. Okay, now I've got my r value, and I already knew that the x value was equal to -4, the y value was equal to +3, and so now take a look at what happens when I find sine and cosine for theta. The definition of sine, if we go back, the definition of sine is the y coordinate divided by the r value. So the sine of theta is going to be the y coordinate divided by the r value. The cosine of theta is going to be equal to the x value divided by the r value. So we get to an interesting result here, which is the fact that, first of all, for sine and cosine, the numbers are different, but perhaps more importantly, one of them is positive and one of them is negative. So that's going to have meaning. That's going to become more and more important as we move on. Right now, that's just a curiosity. That's just an interesting observation. And I'm using that new definition. Technically, what I just did here did not rely upon me making that triangle. I could have just left it this way because of this new way of defining things. The fact that the sine and cosine and tangent of theta, they actually have now nothing to do with the triangle itself. The triangle is just a tool we use to figure out what's the opposite, what's the adjacent, and what's the hypotenuse. Okay, so let's move forward from there. Another scenario, kind of similar to what I just did. I'm just representing things a different way. So imagine, if you will, I've got some point A and B. Now if it helps you, you can think of this as being, for example, the point 3, 5. Well, that would mean that the point Q, which you can see here has a negative A, so in that case, the point Q would be, for example, -3, 5. And that's perfectly fine. So just, I want you to understand, this abstraction is not there to try to confuse you. I'm just trying to be very general. So in an acute triangle, that would be my angle theta. And that would mean that if this triangle, which is a right triangle, if this triangle has the angle theta there, then this right triangle, this green side must be the same as this green side, because even though one is positive and one is negative, the length of them is the same. And remember, when you're talking about triangles, we only have positive side lengths. This blue side is the same as this blue side, which means this is also the angle theta. So these two triangles are just mirror images of each other. But what we're actually really interested in is actually this angle, which is an angle in the Cartesian plane. Here is the initial arm out here to the right. Here's the terminal arm. And because the x-axis forms a straight line, this must be 180 degrees minus theta, because these two things together have to add up to that straight line, which is 180 minus theta. So how can we relate these things to each other? Just reminding you again, the definition said that the sine of theta is equal to the y-coordinate divided by the r value. Now, I don't know the r value yet, so I should start with that. So I'm going to write that r squared must be equal to the x-coordinate squared plus the y-coordinate squared. So what is the x-coordinate squared? That would be, for this acute triangle, the x-coordinate was a. So this would be a all squared plus, and then the y-coordinate was b, and that would be b all squared. And so I end up with r is equal to the positive square root of a squared plus b squared. And the reason for that, of course, the reason why it's positive is, of course, we know that r must be greater than 0. How else could I have done this? I could have also, if this green and this blue was the same as this green and this blue for length, these r's should be the same. But if I use this definition is not about triangles, this definition is about coordinates. So I could have also used that r squared is equal to the x-coordinate for the obtuse angle is negative a, but that's still all squared, plus b squared, but of course negative a all squared is just a squared, and b squared remains b squared, and I take the positive square root of that, and that's r, and not surprisingly, my two values of r are exactly the same. So now I have my value of r for both of these. So what is the sine of theta? The sine of theta is the y-coordinate divided by r. What was the y-coordinate for the angle related to theta? That would be, the y-coordinate is the letter b. So that would be b divided by r. r is the square root of a squared plus b squared. What is the sine of 180 degrees minus theta? Well, 180 minus theta is this obtuse angle, and the definition of sine is the y-coordinate divided by r. For, in this case, the terminal arm's point has a y-coordinate of b, just like this one did. And so we end up with, once again, and this is a pretty surprising result, b over the square root of a squared plus b squared. These two things are actually equivalent. They are the same. So we end up with this interesting conclusion. Therefore, the sine of theta is actually the same as the sine of 180 degrees minus theta. It turns out that for an acute and an obtuse angle, since sine only depends on the y-coordinate, then if those two angles are what we call supplementary angles, meaning that the two angles together add up to 180 degrees. If that's the case, then we end up with B. Just need to check one thing here. Okay. So that's where we're going to start. The first conclusion we get, and this is important. So this is the first conclusion we get from this, which is that the sine of an acute angle is the same thing as the sine of an obtuse angle. All right, this is the exact same setup we had before. And so now asking the same questions, here's the angle theta, which means this is the angle theta, which means this is the angle 180 degrees minus theta. How about cosine? What's the definition of cosine? I'm going to just write it down here from memory because you're going to want to know these things. So the definition of cosine is the x-coordinate divided by r. And I know that students are often intimidated when they're told to know or to memorize something, but you don't really have to memorize it. You need to understand it. The understanding of this comes from this very simple diagram. These are right-angled triangles. And if you can reproduce this diagram and identify the opposite side and the adjacent side and the hypotenuse, then you can come up with sine, cosine, and tangent. So cosine of theta is x over r. The length of r, we've already covered, is the square root of a squared plus b squared. And now that I've got those, let's see how those end up being applied in this case. The cosine of theta in this case is the x-coordinate, but the x-coordinate in this case is a, divided by the r value, which is a squared plus b squared square rooted. The cosine of 180 degrees minus theta, so now this is the cosine of the obtuse angle, is equal to, what's the x-coordinate? Now the x-coordinate is negative a, divided by a squared plus b squared square rooted. So we don't end up with equality like we did before. The conclusion we end up with here is that the cosine of theta is equal to the negative cosine of 180 degrees minus theta. So the cosine of an acute angle is equal to the negative cosine of the supplementary obtuse angle. Or another way I could write this conclusion would be that I could also write it as the negative cosine of theta is equal to the positive cosine of 180 degrees minus theta. Either of these work. So that is my conclusion for this page. All right, now let's move on to something that's a little bit more practical, a little bit more in line with how you'll be using this on a regular basis. Those results that we got are very important, but let's take a look at this in terms of something you're going to be doing quite commonly. Express each of the following in terms of the related acute angle and then confirm your answer, meaning calculate the result. The sine of 125 degrees. Those of you in my classes or following along with my videos know that I'm a big fan of diagrams to help out here. 0 degrees, 90 degrees, 180 degrees, 125 is going to be here. So here is the value 125 degrees. It says write each of the following in terms of the related acute angle. Well, let's find that now then. The related acute angle would be here. And as you can see, we were talking a lot about supplementary angles. Here is a supplementary angle, and that's the relationship that we use. The related acute angle plus 125 degrees must be equal to 180 degrees. They're supplementary. or the related acute angle is equal to 180 minus 125, which is 55 degrees. So there's our first step in this case in answering this particular question. Now we can make use of, we had a relationship before which said that the sine of theta is equal to the sine of 180 degrees minus theta. Those ones are equivalent to each other. So in this case, that should mean that the sine, I'm going to write it the other way around, so that's the same thing. I could write it this way, that the sine of 180 degrees minus theta must be equal to the sine of theta. That's also true. Either of those is fine. And so how am I going to use that here? In this case, that means that the sine of, we started with 125 degrees, must be equal to the sine of 55 degrees. Now you might look at everything I've done here and wonder, well, what's the point? What's the use of that? The use of this is that I was able to take sine in terms of an obtuse angle, and I was able to express it in terms of an acute angle. And this is going to turn out to be actually quite useful as we move forward. Now I was also instructed to verify this. So let's go ahead and do that. If I go to my calculator and calculate the sine of 125 degrees, I end up with 0.8192. Rounded to 4 decimal places. And not surprisingly, I'll be very surprised, but I'm going to be honest, sine of 55 is equal to approximately 0.8192. So that means that this statement is correct. And although that does not prove what we had up here, it verifies that what we came up with before has been verified by this particular experiment or calculation. Okay, how about cosine? Let's do the same thing. First of all, quick sketch. You can see I'm not being too careful here. It is just a quick sketch. Between 90 and 180 would be over there. 160 degrees, I'm going to change the color here. There is my obtuse angle of 160 degrees. Here is my related acute angle. Now this one is quite simple. You might just go straight to your answer here and that would be fine. How do we get that? The related acute angle is 180 minus 160, which is equal to 20 degrees. So this is another way. You could write it as a supplementary angle theorem, or you could just write it this way. And now, what was the expression we had for cosine? We had that the cosine of theta is equal to the negative cosine of 180 degrees minus theta. This one had two forms. Or, and I'm going to actually switch the order the way I did over here as well. So, or the cosine of 180 minus theta degrees is equal to the negative cosine of theta. The negative sign can go on either side. You just multiply through by -1. And you can switch whatever's on sides of your equal sign just as easily. So in this case, what is this actually saying? It's saying that the cosine of 160 degrees, which is what we started with, must be equal to the negative cosine of 20 degrees. We can go ahead and verify that. I'll leave that to you. Put that in your calculator and you're going to find that each of them, well, you know what? I think I have to do it. The cosine of 160 degrees is equal to, and I want you to do this as well, but you'll see that the cosine of 160 actually ends up being negative 0.9397. And that's approximate. And then the negative cosine of 20 degrees, which is going to be the negative of the cosine of 20 degrees, so I'll do it that way. So the cosine of 20 itself is 0.9397, but of course we had to include the negative in front, and we end up showing that it is indeed equal. Now, what about going the other direction? And this is where things get really quite interesting. The sine of theta equals 0.25. Up until now, if you've done this using right angle trigonometry, you would have just said, okay, well, if the sine of theta is 0.25, then theta itself must be the inverse sine of 0.25. Theta must be equal to the inverse sine of 0.25 equals 14 point, and I'm just going to go ahead and round this, 14.5 degrees. And that's approximate. But we have a relationship that says that the sine of theta must be equal to the sine of 180 degrees minus theta. And so that raises an interesting question, which is, hold on, if the sine of theta is equal to the sine of 180 minus theta, that means the implication of this is that the sine of 14.5 degrees is the same as the sine of 180 degrees minus 14.5 degrees. And so that means that the sine of 14.5 degrees must be equal to the sine of, and what's that going to be, 165.5 degrees? And so we actually, in this case, therefore, theta equals 14.5 degrees, or approximately, or theta is equal to approximately 165.5 degrees. And that's interesting. I ended up with two answers. I ended up with an answer that is an acute angle. I ended up with an answer that is obtuse. And both of these are valid. Both of these are correct answers to sine theta equals 0.25. When you do this calculation in your calculator gives you the acute angle answer, but not the obtuse. But we have learned that in some cases, they are the same, so we have to consider both. Now, that's not always the case. Things get more complicated. The cosine of theta equals negative 0.87, which means theta is equal to the cos inverse of, negative 0.87. When I put that into my calculator, I end up with approximately the inverse cosine of 0.87 gives me, oh, I didn't do negative. The inverse cosine of negative 0.87 gives me 150.5. I'm just going to go ahead and round it. Now this one is the obtuse angle. The fact that this gave me the obtuse angle right away, that means that there is no acute angle. There is no acute response, or no acute answer, I should say. Now, why is that? The reason for that is because the cosine of theta is equal to the x-coordinate divided by the r. If this is negative, cosine theta equals negative 0.87, that means that x over r must be equal to negative 0.87. But what can you always tell me about the r value? The r value is always greater than 0. So in this case, what is this saying? Therefore, the x-coordinate must be less than 0, because the x-coordinate must be the negative part that makes this ratio negative. But if the x-coordinate is less than 0, then where does the point have to be? It can't be over here in quadrant 1. It has to be over here in quadrant 2, which means the terminal arm must look something like that, which means the angle must look something like that, and in this case, that would be an obtuse angle. Now that I have explained that for cosine, bring that back over here for sine. Sine theta is equal to y over r. That means in this case it was sine theta equals 0.25. So that means that y over r must be 0.25. R is greater than 0. So if r is positive, what can we say about y if we ended up with a positive ratio? Y must also be positive. Well, what does it mean for the y coordinate to be positive? That means we could have a point here, but we could also have a point here. Both of those points have positive y values. And so we end up with theta or theta. Actually, let me write that as, instead of theta or theta, because technically this one would be 180 degrees minus theta. Okay, but they're both valid answers because both of them have a y coordinate that is the same positive number. That is conceptually very difficult to get your head wrapped around the first time you see it. So please take your time on this and think about it. And that is it for this lesson. Lots of practice there. I cannot stress enough how important the related acute angle practice is. We looked at this in the previous lesson as well. Once again, I invite you, if you need more RAA practice, let me know. I can generate lots of these very quickly and easily. And you do need to get to the point where you are getting this more than 99% of the time. Everything you do will depend on you getting this correct.